In this video, we'll cover the problem max area of island. Here, our input is going to be a 2D array of zeros and ones. Zeros are going to represent water, and ones are going to represent land. So you can see that we are forming some islands by groups of land that are connected in certain ways. What we need to do is return the area of the largest island. And the way islands are connected is only going up, left, down, and right, not diagonally. So I'll circle or outline all of the islands we have here. So these are our different islands. The important point being, these three on the left are not a single island together. They are not connected because we don't count diagonal connections as valid. We only care about up, left, down, and right. So you can see that these three islands over here have an area of 1. This island at the bottom has an area of 2. And this island over here has an area of 4. So the area is just how many ones are present inside the island. So you can see the largest island has an area of 4. It is this one over here. And so we would output 4. Okay, so the first question you might have when you see this is, how is this a graph? I've put it in the graphs category, specifically under BFS. How is it a graph? Well, remember, a graph is a bunch of nodes that are connected in some way. So the question said, we only care about connections that go up, left, down, and right. So if we look at this particular number, this one right here, we care about up, left, down, and right. So we can really think of it as this one is a node, and there are edges going up, left, down, and right. And these are going to be undirected edges because you can also go from 0 to 1 because you can go to the right. So we have really an undirected graph here. And a lot of times you'll get these grid questions where you're really dealing with an undirected graph. It's just not phrased that way or framed that way in the problem. Okay, so we understand how this is a graph. Now, how do we actually solve this question? Well, the approach and the reasoning is actually very similar to the question count friend groups. When we hit a particular node, so when we hit this node, what we want to do is traverse the entire portion of our larger graph that is connected to that node. So in this case, it means we want to traverse this whole section. And we want to do two things. Number one, we want to mark it as visited. That way we don't have to try to start another search from this node and from this node and from this node because they all are part of the same island. But the second thing we want to do is we want to figure out how big is the island, right? Because that is how we really figure out the largest island. We have to figure out the size of each island. So we can use a very similar strategy to what we did in count friend groups, where every time we hit a node that hasn't been visited, we BFS through that portion of the graph. We will mark every node in that graph as visited, like we've done before. But in addition that we will do is that we are also going to count the size of that island. And then when we're done, we're just going to compare that versus the max island size we have so far. Okay, so that is like the approach. We're going to do pseudo code in a moment, but before we do, I want to point out one thing. The way we know that we should use a BFS here is that we want to traverse through an entire portion of our graph. Not the whole graph, but an entire portion of it. And we've discussed before that anytime you want to traverse an entire portion of a graph, one way to do it is using a BFS. Okay, now let's go ahead and pseudocode out how our algorithm is going to work. We want to check every single point. So we're going to iterate through every point. So let's start with that. Iterate through every point. And when I say every point, I mean every position in the 2D grid that we receive as our input. So all of these individual ones and zeros. Then what do we want to do at each position? Well, we know that if it's visited, we want to skip it. right? We don't want to, if we start a search from here and we figure out 4 is the island size, we don't need to search from here, here, and here. They're all going to give us the same island. So we know that if a node has been visited, we skip it. But the other thing is if it's a 0, we can also skip it, right? Because that's water. Clearly, water is not an island. Only land can be part of an island. So we can say visited. If it's visited or 0, we just skip it. Otherwise, that means if we get to this point, we know that we have something that has not been visited and it's a 1. So it is a new island. So what we want to do is get the size of this island. So we'll say get island size. And this is where we're going to use our BFS. And as a quick note, here in this step, we also want to mark every node. We can say mark the whole island as visited. So mark island as visited. That's like sort of a side effect of this step that we need to make sure happens. And then the last thing is once we have the size of this island, all we want to do is just check, hey, is it bigger than the max size we've seen so far? So we'll just say update max island variable. So that if this value is greater than what we've seen before, we want to, overwrite it. If it's not, then we don't need to. We can say update max island variable. I started writing that as if it was code. Okay. So this is really the idea of the algorithm. Obviously, get island size is going to be a bit more involved, but we'll get into the nitty-gritty there in the code. All right, so let's talk about the complexity here. Okay, complexity. So we will initially define our variables. A lot of people, when they have a standard problem, like a grid problem that has 2 variables, they'll use m and n as their variables. I personally don't like that. I think it's a little bit difficult to hear the difference between m and n, especially if you're doing a virtual interview and it's not in person. It's very easy for them to sound the same. So I personally prefer to use r and c. So I'm going to define r to be the number of rows in our grid, and we'll define c to be the number of columns in our grid. It really doesn't matter. If you prefer m and n because it's what you're familiar with, that's totally fine. Just make sure it's very clear which one you're saying. I prefer r and c. I think it's very difficult to mix those two up. So our time complexity is going to be O of r times c, and our space complexity is going to be the same. R times c, and then space is the exact same thing, which is r times c. So let's talk about why each of these are. Okay, so for the time complexity, clearly here we're iterating through every point. How many points are there in our grid? Well, it's going to be r times c points, right? Because we have r rows right here. And that was done poorly. R rows. And then we have c columns right here. So there are r times c points that are present here. So that already tells us that we are O of r times c. But you may be thinking, hey, we're doing a BFS right here at every single point, or we could, in the worst case, maybe. And the BFS maybe is its own r times c, so maybe it should be O of r squared times c squared. Well, that's actually not the case, and here's why. Our BFS makes it so that we should only ever touch a node twice. Let me show you what I mean. If we're iterating in order, we hit this point, and then we explore this entire graph. So this entire portion of our graph. So these 4 nodes here. Then we continue iterating, and later on we hit this one more time, and we skip it. But we don't hit this value here. And then we iterate on to here, and we see, oh, it's already been visited, so we just skip. So I'm counting, the fact that we skip is still some work. And then we come here, and we say, hey, this has been visited, we skip it. So what you see is it is impossible for us to ever touch a single node more than twice. In the absolute worst case scenario, if our entire graph or entire grid was just a bunch of 1s, what would happen is this. First, we would hit the top left corner, and we would BFS through the entire grid. So we've just touched every node once. Then we iterate through the rest of the graph, skipping every single node. So we touch every node one more time. But the absolute worst case scenario, we touch every point twice. So our time complexity would be O of 2 times r times c. but we know that we can drop constants in complexity because they aren't that important. So we get overall O of R times C time. In terms of the space, it's also O of R times C, mainly because of the visited array, right? Oh, I should have mentioned that. I'll mention that right now. But the way we're storing our visited array is we're going to store a 2D array that looks identical to this. The only difference is we're going to store Booleans at every position. That way, we can figure out, like, the top left corner of our visited array corresponds to this element. So row 0, column 0 in our visited array will have a Boolean. If that Boolean is true, it means this one has been visited. If the Boolean is false, it means this one has not been visited. If that's not clear, I think it'll become clear as we start to code it out. The idea is we basically copy this input grid, and the corresponding location for this number tells us whether this number has been visited. So since we're copying our grid, the number of elements we're going to have in our visited array is going to be R times C. And so we get the space complexity here of R times C overall. That's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've imported a queue. I've brought our input here, which is this 2D grid. And we have our output, which is the max area of an island, which is 4. So let's start by just writing out our test as we normally do. So we'll put our input as this array here, and then we'll just print out get max area of island, and we'll pass in the input. Okay, so now we want to define that function. So we'll call it get max area, and it's going to take a grid, and we're going to want to do something with it. Now, the very first thing I like to do anytime I'm dealing with a grid is I just like to grab the number of rows and columns, because it's a little bit annoying to constantly do grid.length and things like that, and I don't think it's very clean either. I think this is more readable. So we can just say grid is 0.length, and we're kind of assuming that every row has the same number of elements, or every, it's just a fixed column size. There is one edge case here, which is that if we're given an empty array as our input, this is a problem. Grid at 0 will be undefined, and then we try to do undefined.length, and that doesn't work. So we'll just handle the edge case right here quickly. That'll just be, hey, if the number of rows is 0, we just want to go ahead and return 0, because we know the max area of an island is 0 since there are no islands. Okay, now we mentioned we're going to have a visited array, a 2D array that looks just like this one, where each location tells us whether the corresponding location in our grid has been visited. Now, to create a 2D array, or let's do this. We'll write a function here called create array of size, and we'll pass in a number of rows and columns. So we'll pass in the number of rows and columns of our input. The reason I made this a separate function is it's unfortunately not very clean to do this in JavaScript. There is no super nice and elegant way. So I just want to make it a separate function so that it's very clear, here's what we're doing. We're creating an array of this size. So the way this is going to work is we'll create an array. It's going to be new array of size rows, and we'll return this array at the end. Now, each element of this array is going to be another array. So we'll say, all right, iterate through the array. So we'll say I is less than rows, I plus plus. So we're saying iterate through every element of the array, and then say array at I. So set the current element to be a new array that has as many elements as columns. This is just a standard thing. This is how we're creating an array of this many rows and this many columns. So now we have our visited array. Let's also create our variable that's going to be max island area. This is going to be what we'll return at the end. So let's start with 0, and we'll return this at the end. All right, now we want some logic in here that's going to figure out what the real max island area is. So we want to iterate through every point in our graph. So let's do that. So long as row is less than the number of rows, row plus plus. Some people like to use I and J here. I personally don't. I think it's a lot more readable if you use row and column like this, especially something like row is less than num rows. I think that's very clear, as opposed to something like, I is less than, or like J is less than grid at 0.length. This doesn't take any time to understand. That takes a little bit of thinking, so I prefer to do it this way. It's not a huge difference, though. Okay, now each position, we said that if either the position is visited or the element is 0, we want to skip. So let's grab a current element. So let's just say current element is going to be grid at row at column. And we said if visited at row at column is true, because remember, we use the same indices in our visited array because a spot in the visited array corresponds with the same spot in our grid. So if we have already visited this spot, this location, or the current element is equal to 0, because if it's water, we don't do anything. If either of these things are true, we just skip it. We don't need to do any sort of counting here. Otherwise, at this point, we can assume that if we hit line 42, it means that this position has not been visited and it is a 1. So it's a new island. And what we want to do with a new island is we want to say like the current island area is going to be get island area. Yeah, and we'll write this function in a second and talk about what arguments it takes. But let's, for now, assume it gives us the area of that island. Then we just want to say max island area is going to equal math.max of max island area and current island area. All this is saying is that if the current island area is greater than whatever is currently in this variable max island area, let's just overwrite it with the value of current island area. But if current island area is not greater than what we already have, then just stick with what we currently have. We don't need to overwrite it. That's all line 43 is doing. Okay, so now we have this function on line 42 that's saying get the area of this particular island. And if you remember from the approach, a side effect of this function should be to set every node in that island as visited. So we'll have to pass in a few things. We need the grid so that we can, traverse our graph. We'll need the current row and the current column. And we're also going to need that visited array because we said a side effect should be to update that visited array. All right, now let's write this function. So it's going to take a grid, a row, a column, and visited. And here's where we're going to do the actual BFS, right? Because we want to traverse an entire portion of our graph. So for this piece, we want to say, let's create our queue. It's going to be a new queue. And what do we want to do? Well, we first have to add something to the queue. Now, this is important. We can't, if you try to think about what we store, maybe we could do grid at row at call. Well, that doesn't make sense because this is either a 0 or a 1, and we can't really tell the difference between all the different zeros and all the different ones in the graph. We need something that uniquely points us to one location in the graph or the grid. And the only way we can do that is with a row and a column. So we actually have to store two pieces of information at every element inside of our queue. We've done this previously using a class. I mentioned that we can also do it using an array and an object. To be a little bit diverse, here I'll go ahead and use an array. So every element in our queue is going to be an array containing the row and the column. Okay, now we want to do our standard BFS, which is going to be so long as the queue has some elements in it, we want to say grab out the current row and the current column from the queue. So we'll just say queue.dequeue here, just using some destructuring. Then we want to process the current node. We'll come back to that. And then here we want to add the children of that node. So this is where things are a little bit different from what you might be used to when we are dealing with a grid problem. Because we said the children are up, left, down, and right. So it's not as simple as normal. And the reason is because we can't just do dot children and then, or children.for each or something like that. Instead, the way we're going to handle this is we are literally going to pass in the coordinates for up, down, left, and right. So let me show you what I mean. So we'll say q.enqueue. We want to pass an array here that'll have our current row and our current column. But we have to modify these values. So let's say we're right here. If we want to go up to here, then the column stays the same, but we go row -1, right? Because this would be row 2, this would be row, and this would be row 1. So we're saying current row -1. So we'll come back here and we'll say we want to do current row -1. So this is saying go up. Then we want to do something similar, and we'll say current row, current column. And now we want to go to the left. So go to the left, or to go to the left, we say the row stays the same, and we go to one less, column -1. So we'll say, I keep over scrolling, current column -1. and we'll say go to the left here, and then q.enqueue, we will pass current row, current column. And what's different this time? We want to go down. So we'll say hold the column to be fixed and do row +1. So we'll say current row +1, and this is going down. And lastly, we want to go to the right. So that's going to be current row, current column. And if we come here, we want to go to the right. So that's saying hold my row to be fixed and then do column +1. You may think like, it's overkill for me to keep going up to the top and point out like, okay, we hold this column fixed and do this. I have seen so many different situations where people get this wrong. I mean, usually it doesn't end up mattering, right? Because you just take each variable and do -1 and +1, -1, +1. But I'll have tons of times where people will be like, current row -1 is left or something like that. So if you are going to be specifically saying which one is up and that kind of thing, be very careful about it because a lot of people get that wrong. Okay, fantastic. So now we have our standard BFS where we're adding our children to the queue, we're pulling elements out of the queue, and we're initializing our queue. What do we want to do at every node? Well, this function has two purposes. Let me actually write that up here to be very clear. So there are two purposes. One is to make sure that we get the area of the island. So we can just literally the function name. And two is to set the whole island as visited. So we want to do those two things when we're processing the node. So we want to say, all right, let's have some current island area variable. Let's just say island area is going to be 0. And at this position, we want to say, all right, increment our island area. We just found a new piece of the island. So every time we hit a 1, we should be incrementing that island area. And we also want to mark this position as visited. So we'll say visited at the current row at the current column is going to equal true to say, hey, we visited it, this current position. Now, there is a piece of information, actually several pieces that are missing here. If you remember, the way we handle visited information is we have to be very careful to only add things to the queue if they have not been visited yet. Otherwise, you get into infinite loops. We can do that here, or there is a nicer way we can do it, in this situation at least. We can just say, if we ever are about to process a node that has already been visited, don't bump our island area, don't set it to true, and don't add any children. Just skip it. So what we can do is we can just say, hey, if visited at current row at current column is already true, just continue. We don't need to do anything. And that way, even if a visited node will get added to the queue, it will never be processed and it'll never add its own children. It'll just immediately move on. There's also an important point, which is when do we stop? Right? Well, we stop when we hit zeros because zeros should not be incrementing our island area. So we can have another condition here that's going to be if grid at current row and at current column gives us a 0, well, we should also continue because in that case, we don't want to add anything to our island area and we don't want to mark that as visited because it's not a part of this island. This is all great, but there is still something missing, which is, let's say we're at this position right here. Well, we go all 4 directions. And when we go up, our current position is row 0, column 0, 1, 2, 3. So 0, 3. When we go up, we're going to do row -1, so we're going to get -1, 3. And that's not even valid. That's like meaningless. So we have to be very careful to make sure that we don't go out of bounds. So what we want to do is come here and we want to say, hey, if the current row is less than 0, or if the current row is greater than or equal to the end, which is the number of rows, we should continue. This is just saying, hey, if we're out of bounds, whether by being too small or too large, continue. Because the same way we could have gone to -1 right here, we also could have been here and gone down, which has the same problem. It's out of bounds of the array. And we want to do the same thing for our columns. So if our column is less than 0 or our column is greater than or equal to .0.length, which is the number of columns we have, we should continue. So this is fine. This covers the scenarios in which we need to move on from the current position. But there's another important point here, which is that let's say current row is -1. If we're going sequentially, we're going to pull stuff out from the queue, and then we're going to try to go to visited at -1, and that's going to break. This won't work. And then we'll go to grid at -1, and that's going to break, and this won't work. So it's important that these checks to make sure we're in bounds happen first before anything else. And then we only even go into the visited array or the grid array when we already know that the current row and current column are valid. Okay, so yes, I believe this is the main idea for the code. I want to go through the logic one more time. So this part isn't too new, so I'm not going to spend too much time on this function. But basically, we're saying iterate through every point. If it's something that we haven't visited before and it's land, figure out the area of this new island and update our max island area if we need to. And yeah, we have this function here. I'm not going to get into it. It's not too exciting. But this one is like really the core logic I'm going to focus on. We have a lot of pieces that are standard BFS, but we're saying we want to store row and column pairs because we need both of those pieces of information to uniquely identify a position within our grid. Then we're saying grab the island area we'll just set it to 0 and BFS through. And what we want to do is every position we grab out the current row and column. If it's out of bounds, just move on. We don't want to do anything with it. If it's visited, we don't want to do anything with it. This prevents infinite loops. If it's 0, we don't want to do anything with it because that's how we know we're out of bounds. At this point, we know that it is in bounds, it is not visited, and it's a 1, which means it's a piece of our island. So we want to bump up our island area, and we want to say, hey, we visited this position, we should never visit it again. Once that's done, you want to go in all 4 directions, up, left, down, and right, and add those to the queue. Now remember, if they've already been visited, or if they're a 0, or if they're out of bounds, we take care of that here. We don't have to worry about it right here. If you want to, you could totally do all these checks here as well. I think it would get a little bit messy, but it's totally fine. Yeah. So the last thing we want to do is we want to make sure at the end of this function, we return our island area because we're expecting that down here. We're expecting a return value. Okay. Now let's go ahead and run our solution to see if it works. So if we run this, actually, let's see what output are we expecting. We expect 4 is the largest island area. So let's come here, run it, and we get 4 as our output. Great. Okay, now let us talk about the complexity breakdown. So we know that R is going to be defined as the number of rows in our grid, and C is going to be defined as the number of columns in our grid. So our time complexity is going to be O of R times C, and our space complexity is going to be O of R times C. On time complexity, you can see this part alone makes it R times C. And then we talked about how the BFS can only touch every node in the graph once, because after that it's already visited and we shouldn't be worrying about it. So we touch every node in the graph once by doing this, and in the worst case, once again through the BFS. So each, assuming like the entire grid is just once. And in that scenario, you touch every node twice. There are R times C nodes, so your overall time complexity is 2 times R times C. We can drop the constant here, it doesn't really matter for us, so we get O of R times C for our time complexity. For the space complexity, our visited array has the same dimensions as the grid. It has R rows and C columns, so it takes R times C space in terms of the space complexity. That's all for this video, and I'll see you in the next one.